Chapter 8 of Interactive Statistics Methods is on probability. Everything that you have been doing up to this point has been preparing you for this particular chapter and its movements into normality. But in order to understand normality, we first have to understand probability. Now, there are two major areas in terms of probability in statistics and how it's used in the analytical and analysis of data and the analytical mathematical formula regarding data. And those two perspectives are the frequentist, also called classical statistics, and the Bayesian, which uses mathematician Bayes' theorem in terms of looking at statistical probability theories. Now, the most popular and what's most commonly used in what you're learning in interactive statistics methods for the majority of its chapters is the frequentist or classical statistical methodology. Bayesian is used and it is discussed in detail in this particular text so that you have a familiarity with all of the practices in statistics. But for the most part, we're going to talk about the frequentist or classical statistical methodology of looking at probability. So when we look at probability, we're looking at an expected outcome that occurs within observations or data or the acquiring of data as an event, as an outcome, okay? And that is highly critical. So when we begin to look at probability, we can look at P, which is large capital P for probability, in the number of times that a particular stratagem or event occurs, A, the actual event that occurs, and then the number of opportunities in which that event occurs, and that's the capital letter N. So if we read right here what this says, the frequentist point of view of, observes a population mean, and we learned about that in the subsequent chapters, as an existent unknown that can be inferred, in other words, inferring back to our population, and estimated from a sample mean when the sample clearly reflects the population. We mentioned confidence intervals before. So we begin to look at, in terms of probability, how data is derived and what are probable outcomes with that data. Now, the Bayesian definition is provided. You can read that in detail. So in general, probability is broadly defined as the long-term relative frequency, or the frequency in which an outcome or an event occurs. The relative or long-term frequency in which an outcome or an event occurs. So then in the subsequent chapters, we begin to break down mathematically and formulaically what probable events look like, okay? So probability, events A and B, and how they occur. So if you look at, for example, in gambling, how a die is rolled, you know that on a traditional die, you have from 1 through 6 outcomes that occur in a given event the one time that you roll the die. That gives you an example of the outcome, whatever the outcome of the die is, that when you roll it, the event, and the number of times that you roll it is the number of events that it can occur. So it's a 1/6, or 1 out of 6 chance that any of those numbers is going to occur on one given roll of the die. So you have to know the conditions in which the event is going to occur. And those are the examples that are provided in the next parts of Chapter 8. So when we begin to look at probability in terms of distribution and how it applies to statistics, it's important to understand some definitions. So once again, we have some definitions here. Event, experiment, experimental probability, what are fair games, odds, things outcome that you would normally see when it comes to gambling. And that's where much of this comes from. Okay, trying to predict outcomes. Probable, and then Bayesian conditional probability. And the important thing to understand in terms of Bayesian probability is it puts a lot of emphasis on the probability of a given event occurring in which the number of cases or event A are independent and the likelihood, given that probability of that event, that it is going to occur. Okay? So you have the probability of events B and A, And then those are broken down and placed into a mathematical formula. And that is used conditionally to determine and test hypotheses using the Bayes method. So there is more information here on Bayes' theorem so that you can learn exactly what that is and how that's defined. And this is the actual theorem, Bayes' theorem right here mathematically. And the given likelihood of A given B or B given A. Okay? And these are different outcomes. Now you have to have a good idea of how probability occurs because it plays a very important part of determining the outcomes of variables, in particularly when we're looking at the normal curve. So we're going to scroll down here a bit further beyond Bayesian probability and outcomes, and we're going to go rather rapidly here because you can read this for yourself. The video is just aiding you in understanding the principles of probability as it rolls into normality. Now, classical or frequentist statistical probability theory. Okay, so what we have in the sample space, we're dealing with sample space in terms of an experiment and outcomes. And that's how we're testing our hypotheses in the more traditional or classical frequentist statistical probability section of statistics. So things are broken down here. Now remember my example of the die, well, we actually give that here. We have a coin, heads or tails, but here are 6 die, and that's provided here of the 36 sample space possible outcomes if you roll the die twice. And that sample space is provided, and it's graphically represented here so that you have a better understanding of how those particular outcomes, O, can occur in a given time when you have actually set the conditions. The conditions that you set in probability are very important. And these are the basis of the conditions that you would set in an actual experiment. So it's critical to understand that particular perspective because that is what is actually used in statistics. So we provide a table here to show you all of the possible outcomes, where they fall, to give you a better idea of how, in the gambling perspective, and how trends and predictions are used and how probability applies in a sample space. So here we have 3 tosses of a coin. We know that a coin has a heads or a tails. So these are all of the possible outcomes. Showing you that again. All right. And then it explains to you how you would determine those probabilities. And this gives you a good idea. Now, using the sample mean to illustrate probability. Now we give the analytical mean formula here, using summation notation again, rather than the computational formula. All right, that's defined on chapter 6 on page 178. All right, and we begin to talk about how it is defined in terms of adapting it in terms of probability to understand how it actually works in probable form. So the mean of the probability distribution indicating that formula is derived out of the next series of definitions. Of course, here is the mean of a random variable. Random variable is a variable that can occur within the population within a sample space of a particular value, a set of values from whatever that condition set in the experiment and its likelihood of occurring. So that's defined, as well as the population mean variance, all of that in terms of population and in terms of sampling, in terms of how population and samples apply in terms of probability and the likelihood of those outcomes occurring, variables, again, scores, data that can vary, and how you put that into a distribution of scores. Then we begin to talk about randoms. What's a random variable? Okay, has an infinite number of possible variables. Okay, what is a continuous random variable? What does that look like? And this graph should look very familiar to people because it is used with the indefinite interval. And there it is. Okay, and this describes, in this particular space, let me go back to this graph for a moment, where these probabilities are likely to occur. So you see how all of this is beginning to wrap itself together and come together? Now, when you begin to understand probability theory, you begin to get a better idea of how you can infer from a sample back to a population and how the normal curve begins to be built. So once again, as always, so that you understand the different things going on in statistics, we have a lot of definitions here. Read those definitions thoroughly. They're going to give you a more clear understanding of the sample variance, the population variance, the population mean, sample mean, and how they all come together. Now, we have set theories and symbols mathematically that are used that are relative to probability, and in particular to probability and statistics. And as the chapter ends, you're given a lot of those so you understand how they're used. Set theory is a very important part of probability, and understanding that a set of scores is a distribution of scores. So understanding those will give you a very, very good idea of how they are used in statistical notation and mathematically. So read about those, and then we apply those back to probability to wrap everything together and tie things back together. We give an example with marbles and when they would occur in plucking the marbles out of a can, how that probability is given, how it is defined in terms of percentiles. Sample space, and this is why you use set theory. How those different sets interact and what they look like mathematically and how they're shown by Venn diagrams. And then what they look like in terms of probability distributions and how they're defined mathematically. And it's important to know all of this because these are the statistical distributions. When you begin to talk about variables and how scores vary and what's a random variable, you're beginning to set the stage for your experiments and your experimentation that take place with statistics. And the remainder of the chapter talks about the various types of distribution that follow in terms of probability, understanding what they are. And there's a lot of different ones because there's a lot of different ways you can experiment and determine variables. Now, what begins to happen is trials and experiments and understanding as they occur over time, they begin to build the normal curve. The same normal curve, yes, that you use throughout statistics. And understanding that bridges the gap to understanding probability, the acquiring of data, and the normal curve, setting the stage for us to understand normality, which will occur in Chapter 9. So we build all of that to build down into the normal curve, what it means, how the mean applies, what is the central limit theorem, which basically states that the larger a particular sample is, the more it reflects the population, because in any sample, all of the members have an equal chance of becoming a part of the population. And this ends Chapter 8, preparing us at last for normality in Chapter 9.